Hello guys, it's time to learn about one of the most popular attack vectors, that's overflow and underflow. And in this video, I'm going to give you an explanation of how this vulnerability works, how it looks like. And I want to show you some of the high severity issues that I have found. So let's go to it. In Solidity, you're going to mainly use uint data types instead of int, like in many other programming languages. What does that imply? That as you can see in this picture, when you have a variable of type uint8, means that its maximum value is 2 elevated to 8 minus 1, or what is the same, 255. And if you add 1 to 255, it's not going to be 256, but 0. And that is what is known as overflow. As you can see in the picture, this is like the limit, right? So once you add 1 to this, there is no going forward in numbers, but it is kind of resetted to 0. So similarly, if you deduct 1 to uint8 equal 0, so if you deduct 1 from here, and take into account, of course, that uint data type, there are only positive numbers, the result from 0 minus 1 will be 255, and this would be known as underflow. Now, this applies, of course, to all uint sizes, so it's not because it's a uint 8 that it's different. If it would be uint 256, it would work the same way. Now, let's go to, so this is the short explanation. I hope it defines it and it clarifies for you. And of course, make sure to ask any questions. If I can help, I will answer you, of course. So this is based on an article that I wrote, and I will jump directly to the first of the issues. So this is silent overflow. So in general, I'm going to show three main issues. I will go through two of them. First is silent overflow, then it's I will read the title. So you see, the next one is the missing validation for a parameter passed to an external function. So basically controlling always making sure that we check the parameter. And the third one that I want to go through, it's the funds stolen due to an overflow happening inside uncheck. So I'm sure you have heard of unchecked in Solidity. We will go through it as well. Okay, going back to the first one, the silent overflow. So here it is, the first high issue, silent overflow. I took this from one of the reports while studying, and I think it's actually important to know about it. So before going to the issue itself, I gave a little introduction to make sure you know what is a silent overflow. So this basically occurs when casting is attempted from the larger type that holds a value bigger than the smaller type, the maximum value, by using, like for example, in the case above, a wrapper such as uint 128 of the token IDs, which is a uint 256. What I did again, always, I went to Remix. And I wanted to make it as simple as possible and verify what happens. So I created this function. I passed a parameter of uint 16 and I asked it to return a uint 8. So of course the number that I'm going to pass is going to be, it can be bigger. So I passed 1000 and I checked, I deployed the contract in the testnet, and as you can see here, and what it returned, it was 232. So clearly there is an issue there. So it's not going to return the same or the expected value. Okay, let's go to the code, the vulnerability, the code of the vulnerability. So mainly there were in this issue, there were two functions that were involved. It's buy and sell, and they have here the casts that I have mentioned above for the silent overflow. And okay, so in those two functions, there are the two parameters that I have pointed. And those two variables are actually of type uint 128, while the values that update them are of type uint 256. So as you can see above, it might not get, if it's a bigger value than the maximum of 128, it might be corrupted, the response. So as I'm saying here, this means that casting to a lower type is necessary, but this casting is performed without first checking that the values being cast can fit into the lower type. So it's like missing a verification there, right? As a result, there is a risk of a silent overflow. That's how it's called, this vulnerability. In this specific project, the impact that we had is that if the reserve variables are updated with this operation, with the silent overflow, it can lead to break down the xy equal k equation. Basically, I would expect something that it's meant to that it's expected as the constant in this equation, but it will not happen. So, what's the proof of concept of this vulnerability, of this issue? So, in general, well, this is a lot of code. In general, this is just the test that I added, but I didn't get much value from that. I added for extra information. Of course, I will add the link to this article below. And mainly here is saying that it's passing a token with a lot of with a big number for the, what was that? The decimals, yeah, the decimals, 30 decimals. However, okay, let's go forward because the mitigation it's here. So as it's mentioned, it adds checks that the casting value is not greater than the uint 128, that its max value. So yeah, we can see here in this line that it is adding the verification. If this operation is bigger than the maximum of uint 128, it will revert with overflow. And yeah, the same here. And that's how it's mitigated this issue. So with that, we have one of the first examples of an overflow and underflow. The next example is missing validation for a parameter passed to an external function. Again, here is the link that I will share below so that you can see the code itself. And I wanted to specify some option that you have basically on Solidity. That it's, if you want to get the maximum of uint type of data, you can get it in this way, like specifying it the maximum or minimum. Okay, so let's go further. This is the code with the vulnerability. We will be reading more into it, but yeah, keep in mind this receive funds and the uint 256 expiration. As you can see, this function is external, but doesn't have any role controller, anything checking who can access or who can execute this function. Let's move forward. So, okay, here it is. The attacker can specify in the function that expiration is the maximum number of uint 256. So what does that imply? That if this expiration it is added to any other value, it is going to cause overflow, right? So in general, once you identify such a possibility, what I do is I mark it on the code, and then from here on, it is about identifying what's the impact actually, what's the impact on this project, and how can affect the funds or how can affect the functionality and so on. So let's move forward and let's see how it affected this project and why it was raised as high vulnerability. Okay, so in this smart contract, the function fund bounty token allows the depositor to specify which an expiration which is passed directly to the bounty course contract, and it's on receive funds. This is the part where it's updating. Actually, it takes the parameter passed there and it is storing it, right? Then when requesting a refund, get locked funds returns the amount of funds currently locked. The line to focus here is this one, and as you can see, it is adding the stored amount of expiration that it was in that case able to be the maximum number. So this for sure is going to cause an overflow. This line is here inside the condition. So yeah, it's definitely going to happen because it's inside the for and inside the condition. So yeah, let's see what else. So the attacker can cause the get locked funds to always revert by making a deposit in which this operation it's bigger than the maximum of U into 56, causing, of course, an overflow. Now, to exploit this, the user will make a deposit with, as we mentioned before, this as the parameter in the first function in the refund deposit, and yeah, it will always revert, breaking all refunds. Now, about the mitigation, how to solve that or how it was proposed to be solved in this case. It says add the following check to the fund bounty token. And that basically means that this require will check that the amount that we're passing in that unit 256 in the parameter in the fund bounty token function, it needs to be smaller or equal, in this case, to the maximum amount of 128. And that's a way of solving this vulnerability, or more specifically to prevent this vulnerability. So far we have seen the overflow as a silent overflow. We have seen the overflow or underflow in the missing validation for a parameter passed to an external function. So the next one and last in this video is the funds stolen due to an overflow happened inside an unchecked. So I'm sure that you know that the unchecked is usually seen or used when you want to save some gas. That's mainly what we have experienced when doing some audits and we wanted to propose a gas optimization. Now let's learn a bit about the unchecked for those that might not be that aware. So what's the purpose of unchecked in Solidity? So the reason the unchecked keyword exists is to allow Solidity developers to write more efficient programs. The default checked, so whenever we are not using the unchecked keyword, costs more gas when calculating because under the hood, those checks are implemented as a series of opcodes that, prior to performing the actual arithmetic, check for under or overflow and revert it if it's detected. So if you're a Solidity developer who needs to do some math in a 0.80 or greater version of Solidity, you can and of course you can prove that there is no possible way for your arithmetic to under or overflow, then you can surround the arithmetic in an unchecked block. Let's take a look to where was found that vulnerability. And as we can see in this function, we have this huge unchecked. And there is a lot of logic happening inside. This as it is, it would already be a kind of red flag, and for sure it would require a lot of investigation. It might end up being fine, or as in this case, it might have a very big impact and end up being a high severity issue. I'm going to go a bit about it. However, it is the whole idea. It's like this case is not going to be repeated in like generally in other projects, but because it's very specific. But let's go through it and let's see what happened. So in TradeJoe, users can call Mint to provide liquidity and receive liquidity pool tokens and Burn to return their tokens in exchange for underlying assets. That's the main usability. And the user collects fees using collect fees function. The fees are implemented using the debt model. And here is the fundamental calculation fee. I'm not going to get into that, but let's check out these two values here. Here we are mentioning them. They are always increasing, right? And it's okay. It's an ever increasing amount that is updated when swap fees are paid to current active bin. Okay, there is quite some logic being explained here, so it's basically explaining how it's used and where. This is basically that's what it says that it's calling cash fees. Cash fees was used in this here in this function on top. And yeah, let's continue forward. And yeah, let's focus here. The critical problem lies on the condition that is here specified from is not equal to those two addresses. Note that if from or to is the LB pair contract itself, cash fees won't be called on from or to respectively. This was presumably done because it is not expected that the LB token address will receive any fees. It is expected that the LB token will only hold tokens when a user sends LP tokens to burn. This is where the bug manifests. The LP token address and zero address will collect freshly minted LP tokens fees from zero to the current ACC token per share value. They made the proof of concept where are specifying an attack flow. This is a very good approach for the proof of concept, even if you add or implement the code to prove how you can break it, it is nice to add the step by step. So I will share the link as I mentioned before, and you can take a look at the steps or pause the screen and go through it. But yeah, the idea, if we continue forward, that this calculation will create the attacker with the fees collected into the pool. But I am going to continue, I'm going to move further because this part, well, you can read it on your own time because it's a lot of code to be read. And let's go to the impact part. Yeah, so basically the impact is that the attacker can steal the entire reserves of the LB pair. So as I mentioned earlier, once you identify the clear issue, then it's about investigating it and finding out what's the impact, and that's what will determine what is the severity. What is the mitigation for in this case? So the code should not exempt any address from the cash fees. Even address 0 is important because the attacker can collect fees from the 0 address to overflow the fees X or fees Y variables, even though the fees are not retrievable for them. Okay, guys, I'm going to stop here. In this article, I also went through some of the medium issues. Make sure you go through them so that you get to dig deeper into overflow and underflow. So to recapitulate, we have seen the silent overflow, we have seen the missing validation for a parameter passed to an external function, and we have learned that we need to make sure to investigate those unchecked blocks because yeah, they might have, especially when they are as big as this one that we've noticed. So thanks guys. I hope you found this useful. Please let me know if you did, and it helps me know if this type of of a video is helpful, even though I am going through the articles that I wrote. And yeah, please subscribe so that you get to see all the videos I will be uploading in the coming days. And thanks for watching, guys. Take care.